Welcome to the content material for Class 15 of Engineering Statics. You should be watching this video before your 15th class. In this lesson, we will learn how to determine the forces in members of a truss using the method of joints, and how to identify zero-force members. As we begin the second half of the course, we will be looking at trusses. A truss is a structure of slender members joined together at their ends. You can find trusses in roofs and in bridges. When designing and analyzing trusses, we make two important assumptions. First, all the loadings are applied at the joints. Forces cannot be applied in the middle of the member. And second, each joint connection is assumed to act like a smooth pin, so there are no moments at the joints. Based on these assumptions, each member in a truss will act as a two-force member. In other words, the force at each end of the member will act along the axes of the member, either in tension or in compression. Many times, we want to determine the forces in each of the members of the truss. There are two ways to do this: the joint method and the section method. Today we will be focusing on the joint method. In the method of joints, we can look at any joint in the truss and set up equilibrium equations, knowing that each force acts in the direction of the member. The procedure for the joint method is like this. First, look at the truss and identify a joint where there is at least one known force and no more than two unknown forces. For example, at joint B, we see one known force, the 500 Newton force that is applied, and two unknowns, members BA and BC. If a joint cannot be identified like this, such as in this example, then first solve for the reactions at the connections, using the approach we learned for rigid bodies. Then you can start with the connection joint. Second, after choosing a joint, draw a free body diagram for this joint. Draw the X and Y axes in a way that makes the problem easiest. Third, set up the equations for equilibrium using the X and Y axes, and then solve. Once the forces are known, move on to another joint and repeat until the forces in all the members have been solved. Let's look at an example of that. Okay, in our first example, we have a simple truss. So we're asked to find the force in each member of the truss. So what we can do is we can start by using the method of joints by looking at point B. So if we draw point B, and we look at the forces of the members, we have the force of member AB, and I will assume that that is in tension, and we have the force of member BC, I will assume that's in compression. And we have the external force, and I'll call that F1, which is equal to 500 newtons. So now that we have joint B drawn, we set up our equations. So we can start with the sum of the forces in the x direction. Solving for member BC, we find that the force is 707.1 newtons. And the answer is positive, so it means that our assumption that BC is in compression is correct. So we see that force BC is equal to 707.1 newtons in compression. Moving on, we can use the equations in the y direction to solve for f of AB. So, set up our equations in the y. and we find an answer of 500 newtons. Again, our answer is positive, so our assumption that FAB was in tension is correct. So we can say that the force in member AB is 500 newtons in tension. And finally, we only have one more unknown, which is the force in AC, in member AC. So to do that, we can look at joint C. So we'll start by drawing our diagram for joint C. We have the reaction at joint C from the connection, which is a roller. So it acts perpendicular in the positive y direction. And we have force BC, which is in compression. And we'll assume that force AC is in tension. So if we set this up in the x direction, we're able to ignore this reaction since it only acts in the y direction. So we don't have to solve for it, and that's convenient for us. So we'll set it up and solve for this in the x direction. So when we do that, we find an answer of 500 newtons. Positive, so our assumption that FAC was in tension was correct. So we'll write our answer, the force in member AC is equal to 500 newtons in tension. So using the method of joints, we've now solved for all three members in the truss. And we're done. In our second example today, we cannot ignore the reactions. So the first thing we notice is that there are more than two unknowns at every joint. So there's no joint that we can start at. For example, at joint B, we see there are three unknowns. So we can't start there. So it means that we have to solve for the reactions first. So we do that the way we've been doing it so far. Basically, think of the truss as a rigid body, and we'll just look at the external forces. So I'll call that F1 with 3 kilonewtons, and we'll look at the reactions here. This is a roller, so only perpendicular. We'll call that force C, and we have a pin at A. We'll call that AX and AY. So we start by solving our equations in the x direction. AX is 3 kilonewtons. Then we can move on to the y direction. So we see that C and Y are equal to each other, but we don't know what that value is. So we need to use our third equation by setting up a moment, and we can do that about the point A. When we solve, we find that C is equal to 1.5 kilonewtons. And we can go back to this equation up here to find that AY is also equal to 1.5 kilonewtons. So this isn't what we were looking for, but we will need to use this information as we go on to solve for the members that we're interested in. So first thing we'll do is we'll start at the best point. So the best point is probably at point C. Since there's a simple one force direct reaction at point C, we'll start there. So we'll start by drawing point C, joint C, and we have the reaction C. And I'll assume that the force in member BC is acting in compression, and I'll assume that the force in member DC is acting in tension. If our assumptions are wrong, it's okay, it'll just be a negative answer. We'll still get the right answer. So start with our forces in the x direction. And this angle here is 30 degrees, and this angle here is 45 degrees. So, looking in the x direction, we have the x component of BC and the x component of DC. And so we still are unable to solve for that, so we can move on to the y direction. So looking at the forces in the y, well, we have the reaction C, we have the y component of DC, and we have the y component acting downward of BC. So we can use this answer and insert into here. And that's equal to 0, so we can go ahead and solve for f of DC. I prefer to leave all of this until later to compute and put into my calculator. So when I do that, I can find that the force DC is equal to 4.10 kilonewtons. Okay, so I can go back up and I can get force of BC from that and find that that is 5.02 kilonewtons. That comes from this equation up here. So far I've got one answer, two answers. I still need three more. So we're going to have to move on to another joint. So we can go to joint D up here, since that has three of our members that we want. So I'll draw joint D here. And I'm not sure, they might all be in tension. So I'll draw them all in tension. So we have force BD, force DC, which we know is in tension, and force AD, and both of these are 30 degrees. Okay, set up your x and y equations. So we see that AD is equal to DC, which we know already. So it's equal to 4.10 kilonewtons. And we can move on to the y direction. When we solve for BD, we see that the answer is also 4.1 kilonewtons. And there's only one more left. The last one that we don't know is AB. So we can go over to joint A and draw a picture for joint A there. And so we know already the reaction at A, which is AY and AX. And we also have our two forces here, which is member AD and member AB again. 30 degrees and 45 degrees. So everything is known except for AB. We can set up in the x direction. In solving, we find that AB is equal to negative 0.77 kilonewtons. So it means that our assumption was wrong. So I drew it in tension, so it means that's in compression. So the last thing we want to do is we want to write out all our answers. So force AB is equal to 0.77 kilonewtons, and that's in compression. Force AD, and that's in tension. Member BD, member BC, and member DC. And so we have our answer now. There were 5 members. We've solved for every one. So there's the method of joints for us, which is useful when we need to know the force that's in every member of the truss. Before we end today, let's learn a shortcut to make our analysis simpler. Sometimes a member has no loading on it, and we call this a zero force member. There are 2 situations where we can have a zero force member. First, if a joint has 2 members and no external forces, and the 2 members are not in line or collinear, then those 2 members are zero force members. For example, look at joint A. Joint A has 2 members. Members FA and AB are not in line, and there are no external forces applied at the joint. Therefore, FA and AB are zero force members. Can you find another joint with zero force members? If you said joint D, you're right. Joint D has 2 members. They are not in line with each other, and there is no external forces applied at the joint. The second situation that can create zero force members is when a joint has 3 members and 2 of the members are in line, and again if there are no external forces applied at that joint. So in this example, we see that joint D has 3 members. Members ED and DC are in line. So therefore, member AD is a zero force member. Can you find another joint with a zero force member? If you said joint C, you're correct. Joint C also has 3 members attached to it, and we see that DC and CB are in line. There are no external forces applied at the joint, and so member AC is a zero force member. That's it for today. We'll see you in class for the quiz.